Hello, and welcome back to The Explainer. Okay, so if you've been tracking with us, we've already checked off part one, that was our intro and physical properties, and we just wrapped up part two, where we really got into the chemical properties of metals. So what's next? Well, today we are diving into part three of our Class 10 Science Chapter 3 deep dive. We're talking about the chemical properties of nonmetals and ionic compounds. We are literally leaving those shiny, malleable metals behind and stepping into a completely different, but totally fascinating, side of the periodic table.
But before we get super microscopic here, let's just look at the macro world for a second. Have you ever actually stopped and wondered about some of these everyday chemistry mysteries? Like, why exactly do we breathe oxygen? Or why is chlorine the absolute go-to for purifying our drinking water? Why do plants rely so heavily on nitrogen? And oh, here's a really cool one. Why is it that common table salt conducts electricity when it's dissolved in water, but absolutely doesn't do a thing when it's just sitting dry in your salt shaker? Well, today's explainer holds the microscopic answers to literally all of those questions.
All right, let's dive into this. Here is our roadmap for today. Number one, we'll meet the nonmetals. Number two, we'll look at their reactions. Three, we'll explore the atomic quest for stability. Four, we'll see exactly how ionic bonds form. Five, we'll check out the properties of those compounds. And finally, number six, we'll wrap up with a quick revision and a challenge. So, jumping right into section one, meet the nonmetals, essential for life. It is time to get acquainted with the elements that, well, they definitely do not play by the metallic rules we learned about back in part two.
So, what exactly are nonmetals? To put it simply, they're elements that generally just lack metallic properties. We're talking about elements like oxygen, nitrogen, sulfur, carbon, phosphorus, and chlorine. Now, they might not have that shiny luster or the conductivity of metals, but they are absolutely essential for life. I mean, without oxygen to breathe, life as we know it simply doesn't exist. Without carbon, living organisms literally couldn't survive. It's the fundamental building block of life. And without nitrogen, plants just wouldn't grow properly. Basically, our entire world relies on these nonmetals to function. All right, moving on to section two, non-metal reactions, chemical properties. Because just like metals, nonmetals have their very own unique ways of interacting with the world around them.
First up, let's look at how they react with oxygen. When nonmetals react with oxygen, they generally burn to form nonmetal oxides. For example, if carbon burns in oxygen, you get carbon dioxide. Similarly, when sulfur burns in air, it forms sulfur dioxide. It's a pretty straightforward combination, right? But the compounds they create have some very specific, really interesting characteristics. And this actually perfectly illustrates a massive difference from our last lesson. Do you remember how we learned that metal oxides are mostly basic? Well, check this out. Most non-metal oxides are acidic. For instance, if you take that carbon dioxide we just talked about and dissolve it in water, boom, it forms carbonic acid. Take sulfur dioxide, dissolve it in water, and you get sulfurous acid. This contrast, metal oxides being mostly basic while non-metal oxides are mostly acidic, is an absolute foundational concept in chemistry. You'll definitely want to remember that one.
Now, what about water? You're probably expecting some dramatic reactions here, but here's the twist. Most nonmetals simply do not react with water at all. Carbon doesn't react with water. Sulfur doesn't react with water. Even phosphorus doesn't react with water under normal conditions. This total lack of reaction is a defining characteristic, and it makes nonmetals way less reactive towards water than their metal counterparts. And you know what? That exact same passive behavior applies to acids too. Generally speaking, nonmetals do not react with dilute acids. The reason for this is actually pretty simple. Nonmetals cannot displace hydrogen from acids. Because they literally can't push the hydrogen out of the way, no hydrogen gas is produced. This inability to displace hydrogen is a major defining difference between how metals and nonmetals behave chemically. Which brings us to section 3, the quest for stability, atomic desires. Now you might be sitting there asking, why do metals and nonmetals even bother reacting in the first place? To answer that, we have to zoom way, way down into the microscopic world of atomic desires. See, everything in chemistry happens because atoms desperately want stability. It's their ultimate goal. And an atom reaches that ultimate stability when its outermost shell of electrons is completely full. To achieve this perfect, complete shell, metals and nonmetals take totally opposite approaches. Metals achieve stability by losing electrons, which then turns them into positively charged ions. So think of a sodium atom just shedding an electron to become a positive sodium ion. Nonmetals, on the flip side, really want to gain electrons, which turns them into negatively charged ions. Chlorine, for example, will gladly pick up an extra electron to become a negative chloride ion.
And this perfect mismatch of desires leads us right into Section 4, forming ionic bonds. Opposites attract. This right here is the ultimate chemical relationship, where the needs of metals and nonmetals just perfectly align.
So the crucial takeaway is this definition right here. When a metal wants to lose an electron and a nonmetal wants to gain one, an actual physical transfer takes place. This creates a positively charged metal ion and a negatively charged nonmetal ion. And because, as we all know, opposites attract, these two ions are pulled together by a super strong electrostatic attraction. This intense bond, which is formed by the complete transfer of electrons, is what we call an ionic bond. Let's actually walk through this atomic matchmaking step by step using common salt. Step 1. Sodium, the metal, loses one electron to achieve its stability, becoming Na+. Step 2. Chlorine, the nonmetal, happily grabs that exact same electron to complete its outer shell, becoming Cl-. Step 3. These newly formed oppositely charged ions, Na+ and Cl-, strongly attract each other. They lock together to form NaCl, that's sodium chloride, common table salt. It's such an elegant, microscopic exchange that creates a compound that is absolutely essential for human life, for preserving food, and even for medicine.
All right, let's shift gears to Section 5, ionic compounds, physical properties. We are zooming back out to the macro level now to see how these microscopic bonds dictate the real-world behaviors we can actually observe.
We can draw a really clean line from the microscopic structure straight to physical reality. Because the electrostatic forces holding these ions together are incredibly strong, it requires an immense amount of heat to break them apart. So, because of that, ionic compounds like salt have very high melting and boiling points. Salt literally only melts at blisteringly high temperatures. Plus, these strong bonds make ionic compounds generally quite hard. But, and here's the catch, they are also brittle. If you strike an ionic crystal really hard, you force ions of the same charge next to each other, they repel, and the whole structure just shatters. Now, here is the answer to that big mystery we opened the explainer with. Most ionic compounds, like sodium chloride or potassium chloride, are highly soluble in water because the water molecules actually help separate those tightly bound ions. And what about the electricity part? Well, solid ionic compounds do not conduct electricity because the ions are trapped in a rigid structure. They're stuck. But when you dissolve them in water to form an aqueous solution, or if you melt them into a molten state, those ions are suddenly set free. They can move around freely, and freely moving charged particles are exactly what allows electricity to pass through. Mind-blowing, right? And understanding these properties isn't just some academic exercise. It is totally foundational to modern life. The formation of ions explains how salts are formed, how batteries generate power, and it drives so many industrial chemical processes. As you can see, ionic compounds have massive real-world applications across the food industry, medicine, agriculture, fertilizers, the manufacturing of batteries, and just countless other chemical industries. Wow, we've covered a lot of ground today. Let's head into our final section, revision and challenge, reviewing today's lesson, just to quickly lock in everything we've learned. So, here is a quick checklist of the core concepts you've officially mastered today. We explored the chemical properties of nonmetals and discovered that they form mostly acidic nonmetal oxides. We uncovered the atomic quest for stability that leads to ion formation, which culminates in the complete transfer of electrons, aka ionic bonding. We saw this in action with the formation of sodium chloride, and finally, we translated those microscopic bonds into the real-world properties of ionic compounds. I'm going to leave you with this final provocative question to really test your understanding. Why does common salt conduct electricity in water, but not in solid form? Think back to the exact mechanism of those moving ions we just talked about. We'd love to hear your explanation, so feel free to discuss it. Thank you so much for joining me for Part 3. Now, coming up in Part 4 of the curriculum, we are going to be tackling the occurrence of metals, exactly how we extract metals from ores, and the incredibly important concepts of corrosion and its prevention. You definitely won't want to miss it. Keep learning, stay focused, and I'll catch you in the next explainer.